All right, welcome back. The next thing we're going to look at, we did differential calculus in probably less than 10 minutes. Now we're going to do integral calculus. Okay, so the integral is basically defined for positive functions as the area under a curve. So for y equaling f of x, let's say it's greater than or equal to 0. Okay, then the integral from a to b of f of x dx equals, and it's defined in Calc 1 as this limit. Okay. All right, where of course your xk star is in this thing, and sort of the picture that goes along with this is that you have a here, b here, your function's doing something funky. Okay, you have like some xk here, actually xk minus 1 the way that I've done it, xk, and you're taking these areas and summing them up. Okay, so you're just summing up the areas of these rectangles. This limit just means you're taking a finer and finer cut. Okay, so it's getting closer and closer to the actual value. Okay. The fundamental theorem of calculus tells us that if we define f of x to equal the integral from a to x of f of, here I'm going to use a different variable, okay? So one of the things that students I've noticed had trouble with is this idea that the variable inside the integral is sort of a counting variable, okay? Sort of like this k here. This k only exists inside that summation. It's the same thing with this t. This t really only exists inside this integral, okay? But now f prime of x, that's going to equal f of x, okay? Also, in sort of the contrast, f of b, which is going to equal the integral from a to b of f of t dt, equals f of b minus f of a. A little bit weird, okay? But this is the way that we're going to this is the way we evaluate integrals, okay? All right, so in this case, actually f of a is equal to 0 the way that I've done it, okay? So really the more or I won't say technical, the more general way is you would define f of x, let's say, not from a, but like from some other point, okay? Let's actually do it. Let's do it from a. All right, but what we would say is that the integral from b to c of f of t dt equals f of c minus f of b. And that makes perfect sense with integrals, because if you think about it, this is going to equal the integral from a to c f of t dt minus the integral from a to b f of t dt. Okay, and that makes sense if you think about this in terms of what our integral represents. Remember, our integral represents the area under some curve. Okay, so we imagine we have b here and, well, actually I have c here and b here. Okay, so what is it that we're saying? From c to b, okay, from c to b equals the area from a to b minus the area from a to c. Okay, all right, easy as pie. And by that, I mean easy as 3.14159, blah, blah, blah. Okay. All right, so this fundamental theorem of calculus that we just have, it relates derivatives and integrals. Okay, so this gives us some specific ones. The integral, or the antiderivative, of x to the n is x to the n plus 1 over n plus 1. And we're going to add a c because the derivative of a constant is always 0. Okay? The antiderivative of sine of x is negative cosine of x. The antiderivative of cosine of x is sine of x. Now, I'll be honest, when I do these in practice, what I normally do is I just put them there and then I just check, hey, is the derivative right? Okay, so I know the derivative of sine is cosine, so I don't need a negative there. The derivative of cosine is negative sine, so oh, I needed a negative there. Kind of counterintuitive, but at the same time it connects with the derivative knowledge that I know we sort of come to first. Okay? Let me write a couple more here. Antiderivative of e to the x is e to the x plus c. Antiderivative of 1 over x is natural log of x plus c. So this one here, I should have said, well, n is not equal to negative 1. And that you would run into that problem, right? If n equaled negative 1, you'd have a division by 0 problem here. So we'd run into that. Okay? All right, I think that does it as far as like our calculus review. I'll see you all in the next set of videos, which starts substitution.